So my plan for today was to talk about kind of 3D graphing stuff. But before we do that, I should ask, do you have any questions, or do you want to see any more examples of the differential equation stuff that we've been doing? Yeah.
Could you go over number 2 on for this week?
Sure. Could you describe it to me?
Some x plus 7y equals equal to the 7x.
Yeah, this is Co-16C. Today is April 12th. Cool. So, okay. You can see that okay? So to me, this certainly looks like it's a first order linear differential equation. I can't separate this by any way. So I'm gonna try and do this. So I'm gonna try and do this showing the work that I think, right? So let's do that. So we know we're gonna multiply this whole thing by an integrating factor, which we're gonna wait to find. And I'm gonna call it I of x, I guess. So I'm gonna multiply everything by I of x. I'm gonna have y prime times I plus 7i times y equal to I times e to the 7x. I meant to ask her yesterday. I was having a meeting with her yesterday. I meant to ask her like exactly what her process is here, but is this how she usually starts with these kind of problems? Okay, and then we know that this side here is or needs to be the derivative of the product y times I. Which means that we need the derivative of our integrating factor to equal 7 times our integrating factor. Now, I will point out, doing it this way is not always going to be super easy, because sometimes when you're solving this next part, finding the integrating factor is actually more complicated. But for a lot of these, we have something relatively easy. We have that our di dx, our derivative of our integrating factor, should equal 7 times our integrating factor. And then we're going to separate variables. We're going to have 1 over the integrating factor equal to 7 times dx. We're going to integrate both sides. We're going to get the natural log of the integrating factor. We're not going to worry about any absolute values. Equal to 7x. We're also not going to worry about any plus c's. And then we're going to exponentiate both sides and get I equal to e to the 7x. Which I will point out is exactly e to the integral of your p of x. Cool. I don't remember where exactly she likes to plug this in. I feel like right now is the time. So what we really have here is that y times e to the 7x prime is equal to e to the 7x times e to the 7x. Seem good? Okay. So then we're going to anti-differentiate both sides. We're going to say that y times e to the 7x is equal to the antiderivative of, and I should rewrite this as e to the 14x, right? Multiply those things together, get e to the 14x dx, anti-differentiate that. We're going to get y times e to the 7x is equal to 1/14th e to the 14x. Let's see. You could do a u sub there, but for e to a constant times x, we usually say, oh, we're going to divide by that constant. And then finally, we're going to divide both sides by e to the 7x. So we could write this in the way I probably don't prefer, as 1 over e to the 7x times 1/14th e to the 14x plus c. And then if I distribute that, I would probably rewrite this as 1/14th e to the 14x divided by e to the 7x is e to the 7x. And c divided by e to the 7x is c times e to the negative 7x. That's how I would choose to write my general solution.
Could you break down a little bit how you learn about integrating into the 14x?
Totally. So what I'm really doing when I integrate e to the 14x is I'm doing a u substitution. But I'm not showing my work. But here's the work that we could have showed. I'm going to let u equal the 14x. And then the derivative du dx is equal to just 14. Isolating dx, we get du equal to 14 times dx, or 1/14 du equal to dx. So then when I rewrite this integral, the dx becomes 1/14 times du. The e to the 14x becomes e to the u. And now when we anti-differentiate e to the u times 1/14, we just get e to the u times 1/14 plus c, I suppose. And then we plug back in that u is equal to, and we end up getting 1/14 e to the 14x plus c. But I would say generally I would encourage you to try to do this piece of it without doing the u substitution. It's generally pretty true that if you're integrating a function that you know how to integrate, but instead of x, you have a multiple of x, you're just going to get the same usual antiderivative, except you're going to be dividing by that multiple of x. So for example, if I was anti-differentiating cosine of 6x, well, I know that the antiderivative of cosine of x is sine of x. So I'm pretty confident that the antiderivative of cosine of 6x is sine of 6x divided by 6 plus c. And that same idea is pervasive, right? If you did the antiderivative of e to the negative 1/8 x, you would end up getting e to the negative 1/8 x divided by negative 1/8, which I would choose to rewrite as negative 8 times e to the negative 1/8 x. Both of these are just shortcuts for u substitution, right? Here for this first one, we could have done a u sub with u equal to 6x. This one we could have done a u sub with u equal to negative 1/8 x. But they're small enough that we often just bypass them. Cool. Not too terrible. Other differential equations questions before we start talking about the 3D graphing stuff. Okay, cool. Yeah, we can always come back to differential equations, but it's kind of funny. So I would say 16C kind of feels like a very kind of like a melting pot of different topics. Like we do some different equations, then we do some 3D graphing and some other stuff, and then at the very end, I think we do some summations and series. So it's a kind of a big mishmash. Let's go ahead and talk about the 3D graphing. So yeah. And I will say the first thing I would say about 3D graphing is Desmos has a great 3D grapher. I would encourage you to play with it. It's a useful tool. It helps you see the things you're actually trying to maybe graph. Because as you are probably aware, none of us are probably going to be as good at graphing something as Desmos 3D would be as good at. Grant might be an exception. Grant, my coworker, is very good at graphing, very nice pictures. He's got lots of them on his website, so if you're looking for nice pictures, that's a good place to look. Also, your textbook probably has some pretty nice pictures of these things. So it's good to see what these things really look like. That said, let's talk about kind of, the various things we do with 3 dimensions. So plotting some points. Plotting points in 3 dimensions can be a little bit wonky. Let's say we wanted to plot the point 2, 4, 6. So there's 2 typical ways of drawing your 3-dimensional coordinate system. The way most people, I feel like most people at this university typically draw it is by drawing it this way. We draw the usual kind of 2D looking coordinate system where the right axis is actually your y-axis, and the one going up is actually your z-axis, and then the one that's coming out at you is your x-axis, which I'm going to draw like that. Occasionally people I see people like tilt it. I don't usually do this, but some people will draw it like this instead. We'll draw it like there's your x, there's your y, and there's your z. And sometimes it's easier to draw it that way to try to graph the thing you're graphing. We'll plot this point kind of in both of these systems. So when you're plotting a point, you kind of just have to make it up as you go along. So I know I have to go 2 in the x direction, 4 in the y direction, and 6 in the z direction. The problem with the x direction is the scale is not going to look the same, right? If I take some length in the y direction or the z direction, it looks like how long it is. But if I take that length and I twist it towards you, that same length, at least if you're looking at it straight on, no longer looks as long. So the marks in the x direction have to kind of be less to indicate the same amount of length. So I'm thinking, and of course I picked x equal to 2. So there's going to be like a 1 and a 2. And then the y marks are a little bit longer. 1, 2, 3, 4. And the z marks are the same as the y marks. So then I'm trying to go out 2 over 4 up 6. So what we typically do is we often end up drawing a little box. So I'm going to go 2 in the x direction, and then from that point, I'm going to go 4 in the y direction. Or, well, actually I went too far there, right? But I'm really just going to draw a line parallel to the y direction. And then from the y value of 4, I'm going to go parallel to the x direction. And that intersecting point there, that's the point 2, 4, 0. I'm going to do the same thing in the other 2 planes. I'm going to go 4 in the y direction and then straight up. Or I'm going to go 6 in the z direction and then straight over. That point there is the point 0 in the x direction, 4 in the y direction, 6 in the z direction. And then I can do the same thing over here. I can go 2 in the x direction and then straight up. Or I can go 6 in the z direction and then parallel to the x direction. And get the point 2, 0, 6. Finally, from any one of these points, I can either go in the one direction I haven't gone yet. So from here, I haven't gone right. From here, I haven't gone up yet. And from here, I haven't gone in the x direction yet. And that point there, that's your point 2, 4, 6. Kind of a lot to draw this, but that's how we do it. You could have done the same thing here. Here, the scale looks kind of less dramatic. We could have gone this way and that way. I should be drawing dashed lines here. That. And then we can go up like this. So when you're doing this, you're kind of always trying to move parallel to the axis that you're moving in conjunction. So like here, I've gone over 4y, and I'm trying to go up 6 in the z direction. I'm going to go up 6 in the z direction, and then go over 4 in the y direction. I find it harder to graph it this way, personally, because at least when I did it this way, 2 of the coordinate axes are perpendicular to each other in the usual kind. And the third one is not. And so then we could continue with this, that, and then like that. Here's the same point, but drawn in this slightly different shifted perspective. Okay, so what kind of things can we do with points in three-dimensional space? Well, we can find the distance between 2 points. And it's kind of your usual, a lot of these formulas we're going to find are your usual 2-dimensional formulas with like just a third part added on. So in 2 dimensions, the distance formula is going to be the square root of the difference in the x's, x1 minus x2 squared, plus y1 minus y2 squared. And in 3 dimensions, you're just going to add on the z part. In 3 dimensions, your distance formula is going to be the square root of the difference in your x's squared plus the difference in your y's squared plus the difference in your z's. Not really all that different at all. So something we like to do with this is then use this to say, I want to find the equation of a sphere with center 3, -2, 0, and radius 4. Well, there's a very general formula for this, but the idea really is that just like with a circle, you're finding all the points that are the distance of 4 away from the center. So really, if we want to think about how this appears, there's our sphere, and the center is the point 3, -2, 0. When I draw a sphere, I try not to draw the coordinate axis system because I find usually placing it in the right spot is challenging. And then what should be true about any point on the sphere, whether it's this point here or that point there or that point down there, any one of these points should be a distance of 4 from the center. So whether it's this point x, y, z, this point x, y, z, or this point x, y, z, it should be true that the distance between a general point x, y, z on the sphere and the center, 3, -2, 0, is 4. Well, great, we can come up with that equation. We're just going to find the distance between these 2 points. So the distance is going to equal the square root of x minus 3 squared plus y minus -2 squared plus z minus 0 squared. And that should equal the actual distance, which is 4. And then we typically don't write the equation of the sphere this way. We usually square both sides and write the equation of the sphere as x minus 3 squared plus, I'm gonna write this as y plus 2 squared plus z squared equal to 4 squared. So let me ask you all, given the following equation, x plus 1 squared plus y minus 4 squared plus z minus 3 squared equal to 25. What's the center of that sphere? What's the radius of that sphere? Don't tell me, write it down. So when the equation of your sphere is written in the standard way like this, the radius is really easy to see. It's just the square root of that number on the right hand side, which is the square root of 25, which is 5. And the center is also easy to see. I always think of it as the x, y, and z values that make each of these things equal to 0. So I'm going to get x being -1, y being +4, z being +3. That's your center. I should also mention the center is not a point on the sphere. It's certainly an important point. We care about it a lot. But if you plug in -1, 4, 3, what's the left-hand side of this equation going to be equal to? 0. And 0 is equal to 25? Definitely not. So worth noting, the center of the sphere is not a solution to this equation. It's still very important. But sometimes we don't like to write the equation of the sphere quite so nicely. So this is the standard form of the equation, but the more general form is something like this. X squared plus y squared plus z squared plus 6x minus 8y plus 4z equal to 13. That's also an equation of a sphere. It's just not written in the usual nice way. But if we're given this, we can also find the center and radius. And I should start off by saying the radius is definitely not the square root of 13. We have to do something to both sides of this equation to make it look nice so we can find the center and the radius. So typically what we do here is we break up all the different variables kind of to be by themselves, meaning I want to separate the x's from the y's from the z's. So I'm going to write x squared plus 6x. And I know what I'm going to do here eventually, so I'm going to leave myself a space. I'm going to say plus blank, and then plus y squared minus 8y plus blank, plus z squared plus 4z plus blank equals, and since I'm going to add something here, here, and here, I'm going to do the same thing on the right-hand side. I'm going to say I have 13 plus blank plus blank plus blank. And then what am I going to add? Well, we're going to complete the square for each of these. So to complete the square for x squared plus 6x, I'm going to add, well, I'm going to take 6 divided by 2, excuse me, which is 3, and then square it. 3 squared is 9. If I add 9 there, I have to add 9 there. And then similarly here, negative 8 divided by 2 is negative 4. Negative 4 squared is 16. If I add it there, I have to add it on the right side. And thirdly, for some reason, this last one always seems to throw people. I don't know why. For some reason, 4 people just are like, they get thrown off by it. 4 divided by 2 is 2. 2 squared is 4. It is plus 16. So when you're completing the square, you are always adding something. Whether or not the middle term has a negative or a positive coefficient, you're taking whatever that coefficient is, dividing it by 2, and then squaring it. And squaring it's always going to result in a positive thing that we're adding to both sides. So now when we complete the square, we have to be a little bit careful here. The x squared plus 6x plus 9 factors as x plus 3 times x plus 3, or x plus 3 squared. The y squared minus 8y plus 16 factors as y minus 4 times y minus 4, which is y minus 4 squared. And the z squared plus 4z plus 4 factors as z plus 2 times z plus 2, which is z plus 2 squared. One thing I've noticed over the years is that whenever you do this, whenever you're completing the square and writing it as something squared, the thing that you have right there is always just the half of that. So half of positive 6 is 3, half of negative 8 is negative 4, half of positive 4 is positive 2. It always works that way. And on the right-hand side, we're going to get, let's see, 13 plus 9 is 22, plus 16 is 38, plus 4 is 42. Not a nice square number. Oh, well, sometimes you don't get a nice square number. And then our center is going to be the XYZ coordinate that makes each of these things 0, which is going to be negative 3, positive 4, negative 2. And the radius is going to be square root of 42. Somewhere between 6 and 7. Cool. Any questions about that? Let's see. Yeah. Yeah. And we could, I mean, I imagine you talked about the midpoint in class as well. It's a pretty, so sure, we can do one more sphere. Let's talk about one more sphere. Let's say we wanted to find the equation of the sphere with a diameter whose endpoints are 0, 1, negative 3, and 6, 11, and 5. So, as we just saw, to find the equation of a sphere, we need the center and the radius. To find the center of 2 points, we're going to find the midpoint of those 2 points. And really, you're just finding the average of the 2 points, right? When you're thinking midpoint, you're just thinking average. And we know how to find the average of 2 numbers. You just add them together and divide by 2. So the midpoint here is going to be, we're just going to average each of the x, y's, and z's. So it's going to be 0 plus 6 divided by 2 1 plus 11 divided by 2, and negative 3 plus 5 divided by 2. And that ends up being, let's see, 3 comma 12 divided by 2 is 6, and 2 divided by 2 is 1. So there's our center. And then to find the radius, you can do one of two things. You can either find the distance between the two endpoints of the diameter and then cut that in half. But I think it's usually easier if your center doesn't have fractions. Like if this had fractions and these two didn't, I'd probably just use those two. But since nothing has any fractions here, I would just find the distance between the center and one of these two endpoints. And I'd probably pick the one that didn't have negative numbers if I had a choice. So I'm going to say that my radius is going to be equal to the distance between the point 3, 6, 1, and the point 6, 11, 5. But again, either point, we could have picked that point. So then the distance is going to equal square root of 3 minus 6. So I would probably choose to subtract in the direction where things are positive, but again, it doesn't really matter. So I'd probably do 6 minus 3 squared plus 11 minus 6 squared plus 5 minus 1 squared. But you could also go the other direction and get negative 3 squared plus negative 5 squared plus negative 4 squared instead of getting 3 squared plus 5 squared plus 4 squared, which ends up being, I think, the square root of 50. 9 plus 25 plus 16, yeah, that's 50. And I wouldn't bother simplifying that, and here's why. If we're just being asked to find the equation of the sphere, well, then my equation is going to be x minus 3 squared plus y minus 6 squared plus z minus 1 squared equal to the radius squared, which I would then just write as 50. So if you got something and you actually have to write the equation of the sphere, don't bother trying to, like, you could just simplify that as 5 root 2, but there's no need. Unless you are specifically asked what the radius of this is and they ask you to write it in the most simplified form possible. No one's really for that. Cool. All right, sure. Fine. You might also ask something like, where, oh, and actually, yeah. So you might ask something like, where does each plane cut the sphere? So if you were to cut a sphere, I like to imagine an orange with a plane, a knife. What kind of shape do you get when you look at like the tops of the surface you're left with? A circle, right? So when you cut a sphere, you get a circle. And specifically, this, so some language things here. The sphere specifically means just the boundary, just the points that are, so it's kind of like, I guess a better analogy for a sphere would be like a ball filled with air, like one of those kind of bouncy beach balls. So if you were to cut it and it didn't like deflate, the circle that's the outer edge would be what you're left with when you cut that sphere with a plane. In math language, a sphere is just the boundary, whereas if someone says you have a ball, they actually mean the sphere and all of its interior. So I would imagine like a bowling ball with the full, assuming like a solid ball, like a cantaloupe or something. I guess it's also a good idea, right? Where there is mass inside that you cut. And if you look at the top of that, it's actually technically not a circle. The boundary is a circle, and then the entire circle filled in is called a disk. So just some language things. We will usually be talking about the boundaries, but I'll try to be very specific with my wording. But the point here is that when you take a 3-dimensional surface and you cut it with a 2-dimensional plane, you usually end up with a curve in 2 dimensions. So if we were to take, and I have to look at this here, see. So if we were to take this sphere, so our sphere, x minus 3 squared plus y minus 6 squared plus z minus 1 squared. If we were to, equal to 50, if we want to find the intersection of this sphere with, say, the XY plane, or in other words, if we're going to cut this sphere with the XY plane, what we're going to do is we're going to replace something with something, specifically the equation of the XY plane. So if you're, and so just for some points of reference here, I'm going to talk about the room like it's your 3D coordinate system, and I'm going to usually refer to that corner as the origin. This, and sorry, and for those of you on Zoom, you can't really see this, I apologize. And I suppose I could try to tilt the camera a little bit, so maybe, yeah, maybe kind of, sure, maybe. So here's the corner over here. The edge going up is your z-axis. The edge along the floor under the chalkboard is your y-axis, and the edge coming out towards you is the x-axis. The floor is the xy plane, because it's the plane who's bounded by the x-axis and the y-axis. And the left wall for you is the xz plane. X-axis, z-axis. And the wall back behind me is the yz. So if we want to find out what's going on in the xy plane, well, if you're on the floor, your height is 0, which means your z value is 0. So to figure out what's going on in the xy plane, we're going to set z equal to 0. Let's see what happens when we set z equal to 0. So that's actually going to work out nice. I happen to have some nice numbers here. Great, I love when it works out nice. So if I set z equal to 0, I'm going to get x minus 3 squared plus y minus 6 squared plus 0 minus 1 squared equal to 50. 0 minus 1 squared is just 1. I subtract 1, I get x minus 3 squared plus y minus 6 squared equal to 49. So in the xy plane, I have a circle. And I should really say, I should use one word. This is the trace in the xy plane. It is a circle centered at 3, 6 with a radius of square root of 49. 7. And I do think it's nice to see what this looks like. So let's graph our sphere real quickly here. Not too terrible. So our sphere is just x minus 3 squared plus y minus 6 squared plus z minus 1 squared. I might have wanted to have picked a center that was a little bit closer to the origin. That's going to equal 50. If you can't see, oh, there, so there's part of it. And then if we wanted to, we could certainly zoom out. Ooh, that's not what it, yeah, zooming out. Am I zooming out or zooming in? Ah, smooth. So we could zoom out a bit. And there it is. There's our sphere. And for this one, you can actually see where it intersects the XY plane really easily because the XY plane is already graphed for you. But if you want to make it more obvious, you could also then say plug in z equal to 0. And there's your XY plane. And then you can click on this button over here, and it'll give you the view where you're just looking at it like you're looking at the XY plane, which is nice. And then I also kind of like to click on this little gearbox here and make my surfaces translucent so you can kind of see through them a little bit better. And then you can kind of see, oh yeah, look, there's the circle we were talking about, where the plane and the sphere intersect. And you could also do this for the other axes as well. So if instead of saying z equal to 0, I set y equal to 0, and I extend it to 3 dimensions, there's my YZ plane. And yo, that's cutting it in a seemingly smaller circle. Let's actually see if that's actually true. So if I were to instead have set, I have enough room. If I were to have set y equal to 0, which is going to give me the trace in the 2 remaining variables. I might have said YZ plane before. I should have said XZ plane. If I set y equal to 0, we're going to get the trace in the XZ plane. Setting y equal to 0, I'm going to get x minus 3 squared plus 0 minus 6 squared plus z minus 1 squared equal to 50. 0 minus 6 squared is 36. 50 minus 36 is 14. Oh yeah, we're getting a circle with a much smaller radius. Right? 50 minus 36 is 14. The radius is a little bit smaller than 4, which is kind of terrible, which is corresponding to the thing we saw in the graph, which is good. And this idea of finding the trace of your surface is kind of what we use to help us actually draw a lot of surfaces. So let's look at some examples that are not this. So let's say, let's look at the following. It's one of my favorite ones. Let's say we have the function of two variables, z equal to 9 minus x squared minus y squared. And I'll point out, so just as a kind of commentary on this, so just like in 16a, we were graphing something, we might have written something like, y equals x cubed minus x. Or you might have decided you would rather have written it as f of x equal to x cubed minus x, where y and f of x are kind of interchangeable. Y is the function, f of x is the function, either way. Well, the same kind of thing is true here. We might write this as z equal to 9 minus x squared minus y squared if we can explicitly solve for z. I wouldn't have done this in the previous one because it's kind of hard or weird to get z by itself. But here we could definitely rewrite this as f of xy equal to 9 minus x squared minus y squared. And it has the same sort of meaning. Oh yeah, we're just saying this z value is a function of x and y. So I'm going to try, you're welcome, yeah, see you later. So I'm going to try and draw this by, let's find the traces. So we're going to find the trace in each of the coordinate planes. So we'll start with the xy plane. And much like how in graphing in 2 dimensions, if you're finding like the x-intercept, you set the other remaining thing equal to 0. The same thing is true here. If you're finding what's happening in the xy plane, you're saying z is 0. So in the xy plane, we're setting z equal to 0. And we're left with 0 equal to 9 minus x squared minus y squared. Typically, when you do this trace finding, one of two things happens. You either want to find y as a function of x so you can see what the graph looks like, or you might have a situation where you have x squared plus y squared showing up, and then we know it's going to be something like a circle. So in this case, what I would do is I would just add x squared plus y squared to the left side and get x squared plus y squared equal to 9. So in the xy plane, my trace is going to be a circle of radius 3. Let's see what's happening in the other planes. So in the, the YZ plane is usually where I like to graph, because in my mind, the YZ plane is the one that's like flat on the paper that's easy to draw things in the right perspective. So for the YZ plane, we're going to set x equal to 0. And we're going to be left with z equal to 9 minus 0 squared minus y squared, which is just z equal to 9 minus y squared. And that looks like a downward opening parabola with a vertical intercept of 9 and horizontal intercepts of plus or minus 3. Doesn't have to be perfect. It's going to look something like this. You'll notice my labeling, though, I'm still including the x coordinate of 0. And then finally, what happens a lot is often the thing that's happening in the YZ plane is also happening in the XZ plane. And we see that if we draw the trace in the XZ plane, we're going to get pretty much the same graph. Set y equal to 0, we're going to get z equal to 9 minus x squared, and that's going to have the same trace. So this point is still 0, 0, 9. This is x, this is z. This point is 3, 0, 0. This point is negative 3, 0, 0. And then if we're actually trying to draw the three-dimensional surface, what we typically do is we kind of like put these three things on our three-dimensional coordinate graphing system and then try to draw the surface that corresponds to that, which isn't too terrible sometimes. So here, I'm going to start off by drawing what's happening in the YZ plane, because again, that for me, that's the easiest. I'm trying to be somewhat precise. So there's my 0, 0, 9. And then you go 3 to the right, 3 to the left. So I know in the YZ plane, I'm going to get this parabola here. And it does keep going, but I'm going to hold off on that for a second. And then I know I'm going to get a circle in the XY plane, but I can't draw it like a perfect circle because it's been laid flat. So I'm thinking about drawing something like this. So it looks like my circle, but sitting flat in the XY plane. So that point there are my other ones. And then I can connect those up and draw in the XZ plane the other downward opening parabola. And it does keep going on forever and ever and ever. So this is a downward opening paraboloid. And it opens down, 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 down. Kind of neat. I think it was like a mountain-ish looking thing. Yeah, what else to say about this? Oh, yeah, cool. We do have one other thing to say about this. So the other kind of thing we often talk about when we talk about three-dimensional surfaces, aside from the traces, are the level curves. And really, if I can find the hand that I was looking for. When you think about a level curve, what you should really think about is like a topographical map. Where if you look at, say, let me grab this. Where's my cursor? It's always hiding. Yeah, there we go. So, no, sorry, I know I have, there's exactly one picture I know I like. There we go. I was showing this to someone else the other day. I was like, yeah, that's a good picture. Where'd you go? Stop, right? Sure. So, come on. There we go. So having trouble grabbing this. There we go. So if you look at this picture here, you can see, so the level curves look like if you graph this two-dimensional thing down here with all these different curves that are representing different elevations of your surface. And so you can say, if we just look at that, and again, I know it's kind of hard to see the numbers there, but the numbers get bigger as you go inward. You say, oh, we're imagining the inner one being at a higher height, and then the next outer one is a slightly lower height, and then slightly lower, slightly lower, slightly lower, slightly lower. So when we draw the level curves, we're drawing these curves in 2 dimensions that are representing what this 3-dimensional surface looks like. So it's kind of like, that's exactly like if we were to take, so right, I'm going to draw some level curves right here. So for example, if, again, our function was z equal to 9 minus x squared minus y squared. If we set, say, z equal to 8, it means we're just going up to a height of 8. And if I find the equation, my equation is going to be 8 equal to 9 minus x squared minus y squared. I would then do the same thing. I would solve for x squared plus y squared equal to 9 minus 8 and get a circle of radius 1. So here's the actual curve at its height, and then we're gonna basically pull that down onto the XY plane. Right. So we get a circle of radius 1. And typically, when you're drawing the level curves, you label them. So we would label this, and for some reason, we wouldn't say z equals 8, we would say that c equals 8. So this level curve is at a height of 8. And then we can do the same sort of thing. So I'll point out actually also that when we do this, we usually don't want to keep doing this. I don't want to be like set z equal to 7, z equal to 6, z equal to 5 over and over and over again. So what we often do is say, well, I'm going to set z equal to c and get c equal to 9 minus x squared minus y squared. And then I'm going to do the same sort of solving I did before. I'm going to get x squared plus y squared equal to 9 minus c, which I can see is a circle. Center is the origin. And the radius is the square root of whatever 9 minus c happens to be. So when c was 8, our radius was 1. If c were to be 7, our radius would be the square root of 2. And let's pick a nicer value. If c were to be, say, 5, our radius would be the square root of 4, which is 2. So we go down to an elevation of, say, 5 here. 1, 2, 3, 5. We get that circle of radius 2, and then we just exactly drop it down onto our c equal to 5. So that, and then let's might as well throw in one more. If we went all the way down to, well, so we could keep going, right? We could go c equal to 0, c equal to negative numbers. As long as c is in the range of your function, it's a valid choice. So if we let c equal 0, the radius of our level curve is going to be the square root of 9 minus 0, which is the square root of 9, which is 3. So down here at the bottom, right, there's our level curve when c equals 0. So we see, oh yeah, at the sea level, right, at a height of 0, our circle is big, and then the higher up we go, smaller circles get. Cool. Talk more about level curves next time.